high voltage push-pull power amplifier circuit is shown in this example and analyzed in this video. This circuit is implemented with one low power low current op-amp as shown here, and then we have at the output stage we have Darlington transistor pair in the form of BJT NPN transistor pair, and we have bipolar junction transistor PNP pair, and then we have current limiting transistors, and then we have just the current source effectively in the circuit that provide the initial current for further amplification. So this is a high voltage power amplifier. Please note the supply voltages that are pretty high, 125 and minus 125 volts. We want to find the output voltage given the input voltage in the form of a sinusoidal signal, for example 5 sinusoid omega t, assuming the frequency of applied signal is in the proper range. We also want to understand how this circuit is working. So these are the things I would like to address in this video. Okay, so let's start from noticing the supply voltages for the op-amp. The positive supply voltage of the op-amp at this node is connected to a Zener diode. It's a 15 volt Zener diode that is trying to enforce that nothing more than 15 volt appears at the positive supply voltage of the op-amp. The same thing with this wiring of this Zener diode 15 volt. Again, we are guaranteeing that despite minus 125 volt here at this node, we will get a proper minus 15 volt here by having this 10 kilo ohm resistor properly connected. So with that in mind, then we have the proper negative 15 and positive 15 volt supplies for our op-amp here, and it's a low power low current op-amp. Look at the connections of the op-amp. So we have input signal Vn applied at the input of this 10 kilo ohm resistor, which is connected to the positive input terminal of op-amp or non-inverting terminal. We also have this capacitor C, for example, on the order of 100 picofarad, that is connected to the negative or inverting input terminal of the op-amp, and also a 10 kilo ohm resistor that is connected to ground. So what happens is when input is increasing, for instance, if we have a sinusoidal input applied, and if you're dealing with the positive cycle of input, what happens is it tries to increase the voltage at the positive input terminal of op-amp, and therefore op-amp at the beginning feels that there is a need to increase the output voltage. So as op-amp is trying to increase the output voltage, then what happens is this transistor that is on the verge of operation is turning off because this voltage is increasing, and effectively with the voltage of base increasing, effectively it will shut down this transistor. And then so PNP transistor turns off, NPN transistor actually start having more current. So this current source here start becoming more active. So more current is now flowing from the base of a PNP transistor here, in the first PNP transistor in the Darlington BJT pair, PNP pair, and then as a result more current start flowing this way, and as a result you will see that we will have a voltage drop like this at the output, which means we are dealing with a negative cycle of sinusoid at the output. So we are here. So when we are at the positive cycle at input, then we are dealing with a negative cycle at the output, and this is a good news. This is an indication of proper wiring in this circuit, because input is trying to, in the positive cycle, input is trying to increase the voltage at the positive terminal. So it tries to jack up the voltage here. At the same time, output tries to decrease because we are in negative cycle. So we are trying to, output tries to decrease, counteracting what input is trying to do. So this is a negative feedback wiring, which is what exactly needed. So negative feedback in this circuit. Okay, so what I'm going to do is, now that we understand overall big picture of the operation of the circuit, let me just simplify the circuit this way. So imagine I have my op-amp, and then we have the connections like this. So we have the 10 kilo ohm resistor, which I refer to it as R, and then connected to ground. We have the capacitor C, which is 100 picofarad, but let's refer to it as capacitor C. And then we have output of the op-amp. From the output of the op-amp, this node, I have some voltage gain up to output. So I'm going to refer to that as just amplifier voltage gain A. and I get to the output. Just bear in mind that as we talked about it, when we are dealing with a positive cycle, here is also going up, but the output is going down, and vice versa. Meaning that when we are in negative cycle at input, this node is trying to go down, but output is trying to go up. So it's not just a gain, it's a negative gain. So let me make sure that that is taken into consideration. So we have negative A, and then we have V out, and as you can see, V out via this node is going back via this wire to the input to basically this parallel cap and resistor. So I have this connection back. So I have this connection back here, and what I have is I have a 10 kilo ohm resistor going to Vn, and then I have the combination of C over 3. So let's say if it is 100 picofarad here, this one is about 33 picofarad, for instance, and we have the 200 kilo ohm resistor, which can be a potentiometer, by the way. If we want to adjust the gain in this circuit, we can make this 200K as a potentiometer, but let's consider as a 200K. So now this is a circuit we can easily analyze, because as we talked about it, there is a negative feedback in the circuit. Op-amp is properly biased, so I can say because of negative feedback and because of proper biasing of the op-amp is in linear region, and as a result I can say virtual short is valid for the op-amp, which means the voltage at the positive input terminal of the op-amp should be equal to the voltage at the negative input terminal of the op-amp. Let's refer to that voltage. This is helpful. Let's refer to this voltage as voltage V. So is equal to V. Okay, so just bear in mind that if this node is V out, this node is obviously V out divided by A and a minus sign, naturally. Okay, but it's obvious a relationship between negative V out over A and V, because op-amp is ideal op-amp. There is no current flowing or coming out of the input terminal, so whatever current going this way should flow completely through the R and C, and basically the C here and this R, they are effectively in series. So I can do a voltage division between negative V out over A at the output of the op-amp and also the V at the input terminal, negative input terminal. So I can say V is equal to the voltage division, which is 10 kilo ohm, or R, let's say, just to simplify it, let's use R, but we know is R in this example is 10 kilo ohm, and then R plus 1 over CS. So, and then this is multiplied by minus V out over A. So just as a note, we say V is equal to RCS divided by 1 plus RCS. And then we have negative V out over A. So let's keep this as an important equation that we're going to use. So let's say equation 1. The next thing I'm going to do is I'm going to write a KCL here. So effectively we wrote a KVL on top, and combination with KCL, knowing that at the negative terminal the current should whatever current going through cap should go through the R. That's basically a KCL at the, or Kirchhoff current law at the negative terminal. We can do a KCL or Kirchhoff current law which says whatever current coming from V in going through 10K cannot go through the input of positive input terminal of the op-amp, and that current should continue. So the current that is coming through 10K should continue through the combination of C over 3 and R, and 20R, let's say, because we are saying R is 10K, so therefore in this circuit 200K is effectively 20R. Okay, so what I can say is, therefore I can write a simple KCL or Kirchhoff current law, meaning that I can find this current by saying it's V in minus V. the voltage drop across this 10K. So I use a KCL at positive input terminal, and I can say it is V in minus V divided by R referred to as this 10K, and equal to, then the outgoing current is the voltage drop across this parallel C over 3 and 200, which means it generates two current. So I can say the incoming current, which is this current, should be equal to outgoing current, which are these two currents. So this outgoing current is the whole voltage drop across these guys. So I can say V, the voltage on left side, and then V out, the voltage right side. So there you go. V minus V out divided by C over 3. Divide by impedance of cap, which is 1 over C over 3S, S domain, and then plus the V minus V out divided by 20R. Okay, so what do we get from this? We can multiply both sides by R, and then what we get is V in minus V is equal to R, and then we have CS divided by 3, and times V minus V out, plus 1 over 20 V minus V out. So that is what we have. Okay, so let me change the color so that it's more visible. What we are getting here is, therefore, we are getting just a little reshuffling things around. I can move this negative V to the other side to make it cleaner. So I have Vn equal to, I have, just trying to make sure I'm not missing something. So I have 21 over 20. That's the effect of negative V and 1 over 20 V. And then we have RCS over 3 times V, and finally we have minus 1 over 20 plus RCS over 3 times V out. Great. What I'm going to do is I'm going to use equation 1 now to substitute for V based on what we have in equation 1. So using equation 1, I can say V in is equal to 21 over 20 plus RCS divided by 3, and then for V I'm going to say RCS divided by 1 plus RCS, and in denominator I have A as well, and we have a negative V out, so I'm going to put the negative here. So I'm going to put the negative here. V in is equal to minus, and what we have is, just to make sure I'm not missing something, we have V out, which I can factor out, and minus 1 over 20 plus RCS divided by 3, and we have V out. So I can factor out, there you go. So we have V out. Okay, so what do we get from this? There is this negative sign for the whole thing, which makes sense because, as we talked about, when we have a positive cycle at input, we get negative cycle at output. So there should be a negative cycle, negative in the transfer function we find for this. So what do we have is, now we can say, if we clean up, we can get V out over V in, which is the responsive or transfer function of this whole thing, is roughly like this. It is A times 1 plus RCS, and then we have, just to clean up, and then minus, of course, and then we have combination of, let's say, I'm just trying to make sure I'm not missing something, 21 over 20 RCS plus 1 over 3 R squared, CS squared, SS squared, and we have plus 1 over 20, and we have A. So let me make sure I'm not missing that one. A over 20, and we have and then we have A times 1 over 3, and let's just make sure I'm not missing something. I think the best thing to do is just multiply rather than just be worried about. So A over 3 R square C square S square plus we have then A over 20 RCS, and finally we have A over 3 RCS. So what we get out of this one is therefore minus A times 1 plus RCS divided by A over 20 and plus, let's factor out everything that has RCS. So 21 over 20, and then we have this component, we have this component, we have this component. So what I can say is it is effectively 21 over 20 plus we can say 23A divided by 60 RCS, and finally we have dealing with these guys. So it's just 1 over 3 1 plus A times R square C square S square, a second order denominator and a first order numerator. So what is the benefit of this? Well, the interesting thing is if we do now, if we just replace S with J omega, so we are doing sinusoidal steady state analysis as expected because we apply sinusoid for this high voltage power amplifier. So we get A plus JRC omega divided by A over 20 plus 21 over 20 plus 23A over 60 RC, let's say JRC omega, so I'm going to keep here, or and then so J is the, just to make sure we are on the same page, J also referred to as I is just the notation for square root of -1. It's just for complex numbers. So 1 over 3 1 plus A, and then R square C square S square is J omega square, which gives us -1 over 3 omega square. So something like this. Now what I would like to highlight is when RC omega is much less than 1, considerably less than 1. Basically what I'm trying to say is when we can neglect all these components. So how can we do that? When RC omega is much less than 1, we can say that these components, when we compute the amplitude of this whole thing, then could be neglected compared to just the real components in numerator and denominator. So the real ones, so let's say this portion of the denominator can be completely neglected because this becomes very small, and the only thing remains, if this is true, the only thing remains in numerator is -A, this portion, and the only thing remains in denominator is A over 20, which give us a gain of -20. That is completely expected. The reason for that is if the circuit is supposed to counteract in the negative feedback, if we apply voltage at input over a 10K resistor and this node supposed to be matching this node, then counteracting that via 20 times larger, so this is 10K, this is 200K, 20 times larger resistor, so that requires 20 times larger Vout to counteract the impact of the Vin. So basically what I'm trying to say is, in sort of a sinusoidal steady state analysis, basically gain of this circuit is, assuming frequency is right, is just defined by 200k divided by 10k and a negative sign. So that's what this analysis is showing, gain of negative 20 in this system. And for this to be okay, it just means that for RC omega to be much considerably less than 1, depends what is the practical level that we would like to satisfy this. Let's say if we are happy with omega is 2 pi f, and if we are happy to say that let's keep this less than 10, less than 0.1. So let's keep this less than 0.1, then it is as if with the values we have, R is 10k, C is 100 picofarad. So this is 10 to the 4, this is 10 to the negative. 10 to the negative, we have 10. So we get for out of this guy. So what we get is, this is 10 to the negative 10. This is 10 to the 4. And hence what we get is 2 pi 10 to the negative 2 pi 10 to the negative 6. 100 picofarad is 10 to the negative 10, and this one is just 10 to the 4, so it gives us 10 to the negative 6. Times f should be less than 0.1, and as a result we get f should be less than, let's say, multiplying both sides by 10 to the 6, we get 10 to the 5 divided by 2 pi. So as long as f is in this range, which is good for an audio amplifier, then we should be all set. And therefore what we can say is effectively, when, just as a reminder, when we are dealing with, for example, with very close to DC frequencies, then this cap is open, and effectively the voltage of negative terminal is defined by just this resistor connected to ground. So effectively setting the resistor at the setting the voltage at the negative terminal to 0 at super low frequencies, and then as a result we have just a gain of 20 that is going in the circuit. So I hope that this review of the response of this power amplifier is helpful in the sense that it shows what we need to be careful, what sort of frequency this power amplifier can work for, and what is the sort of gain we expect in this circuit. For the output stage, what we have is, let's say we want, if this transistor is supposed to turn on, this current limiting transistor, we want 1 milliamp to be able to flow through its collector. If the current gain of this transistor, so let's make the assumption that this is a low current transistor with a current gain of 100. So if the current gain of this transistor is 100, it means when it's 1 milliamp going through the collector, then 10 microamp basically. So just to make sure, 1 milliamp divided by beta 100 means 10 microamp is going through its base. 10 microamp voltage drop across over 1k is nothing. If you multiply 10 microamp by 1 kilo ohm, you just get 0.1 millivolt, or 0.1 volt, which is 10 millivolt. So you get 10 millivolt, which is nothing in terms of what is required for the plus minus VBE voltage drop for this transistor. It's 0.7, but let's say we need just to turn it on. So if we need to turn it on, we need just to apply 0.6, let's say, and the voltage drop across this guy is negligible. So all I'm trying to say is the maximum current that the circuit is limiting the operation to is when so I max times 3 ohm, which is, this is a high power resistor. So let me make sure that I'm not missing something. Okay, so this should be equal to 0.6 volt, which is effectively the voltage drop that is required. The voltage drop that is required across this combination, VBE and the series resistor. So from here we get that I max in this circuit is just 0.2 amp, which is just 200 milliamp. So that is the maximum current that the circuit would allow. And then after that, what happens is when the current is trying to increase more than 0.2 amp at the peak of, let's say, positive cycle, then what happens is this transistor turns on, immediately grab the current that is coming from the current source toward Darlington transistor and grab that current and sort of redirect the current toward its collector, doesn't let the extra current going through the base of transistor. Bias wise, we have a DC current when input is 0. We have a DC current that is flowing here. That DC current can be computed. So the DC current is IDC equal to, say, 0 volt here. Circuit is symmetrically designed, 125 volt here. So we can, the current that is coming this way is negligible because the beta of this transistor, or the current gate, is pretty large, so it's 100. So what we can say is IDC is equal to just 125 volt minus 0 divide by 50k plus 0.5, 50k plus 0.5, which then is just equal to 50 plus 0.5, which is then resulting in roughly 48 milliamp, roughly. So we have 2.48 milliamp IDC going through the circuit, and if that is the case, then multiplied by 0.5k, the voltage drop that appears across 0.5k is, therefore I can say, voltage of base of transistor. Let's say this one is T1. So transistor T1 is equal to 125 minus we have 0.5k, and then we have 2.48 milliamp, which this is effectively 1.24 volt drop. So the voltage drop across this 0.5k is 1.24. We know that we need plus minus 0.7 volt across this emitter base of the PNP bipolar junction transistor. So that leaves us 1.24 minus 0.7. That leaves us with 0.54 volt across this resistor, across 0.33k kilo ohm resistor. So that defines the current that is now flowing toward the collector of T1. So that current is 0.33k, is the voltage drop we found, which is 0.54 volt divided by 0.33k, which, if we calculate that, it is 0.54 divided by 0.33 is equal to 1.64 roughly, so 1.64 milliamp. So this current is 1.64 milliamp, and it's good enough, because if your maximum current that we are providing at the output is this maximum current is, according to what we found, is 200 milliamp. So I'm going to highlight it. If it is 200 milliamp maximum current, this is a high power, this is the most powerful transistor in this circuit that we need to carefully select, but let's make the assumption that it has beta of 20, a very low beta, and this one has a beta of 50. So overall beta of this cascade in the Darlington pair is 50 times 20 is 1000. So 200 milliamp translate to 200 microamp here, or 0.2 milliamp. Let me just put it 0.2 milliamp. That is better to refer to. So 0.2 milliamp. So it's good enough, because what happens is, let me make sure that I'm using the right color. Okay, so it's good enough because what happens is we need a minimum of 1 milliamp through the diodes, a minimum. So we just need 0.2 milliamp to be fed to the base of the Darlington transistor to be able to support the maximum planned current, 200 milliamp at the output. That's all we need. So the fact that we have this current at the collector of T1 being equal to 1.64 is a good sign. It means we have the proper current for the circuit. So basically this is the operation of the circuit. The current limiter works as soon as it turns on, as soon as the current reaches 0.2 milliamp, 0.2 amp either on the upside or downside, and these diodes are the part that support the current sources and then make sure that the transistors, Darlington transistors, are on the verge of turning on so that dead zone is avoided. Basically the idea is output voltage dead zones are avoided. So what I mean by output voltage dead zones, I mean in the output, rather than having, I'm sort of exaggerating, but rather than having this sort of situation, so V out, these are referred to as voltage dead zones. We with the proper biasing that with the proper diodes and biasing that would put the Darlington transistors always on the verge of turning on, because these diodes are like 0.4, 0.7 and 0.7, so effectively they are supporting 1.4 volt, which is matching the required VBE drop across the Darlington transistors. Then we have, instead of this circuit, so instead of this one, we have a near perfect V out without dead zones. It was basically zero crossing issue. These are the zero crossing problems, dead zones, so they are avoided with the proper biasing. That's the idea. I hope that this analysis is helpful in terms of understanding how a high voltage push-pull power amplifier is designed and how it is operating in this circuit, and how we can find the input-output relations and transfer function. Thanks for watching.